Hi everyone, this is Victor, and I'm very pleased to be sharing with you today a bit of our research on zero trust architecture applied to robotics. Before I start, I just wanted to wish everyone out there that you stay safe during this, complicated period, let's just put it that way. And besides staying safe, also secure, actually, and because as you will see throughout this presentation, in robotics, security and safety are extremely connected, and not having one implies very likely not having the other one. In particular, without security, it's very hard to, or impossible, to be safe. So I wish you both, and I wish that you enjoy this short 20-minute pitch. Let me try to make it to 20 minutes because my last three trials recording myself got me to a bit longer. Let's see. Alias, that's where I come from. Alias is a robot startup. We are like 2.5 years old, been in stealth mode for the last 2 years approximately, and we do robot cybersecurity. We've been researching this area for quite a while. Some of us have more than 10 years of experience in the sector. Alias essentially helps roboticists and robot users, as well as manufacturers, to make use of these technologies in a secure manner. We do it offensively and defensively with products and services, and we take a roboticist approach. This means essentially that we use our 10 plus years of experience building robots, from drones to manipulators, industrial ones, to try to help customers make the best use of these technologies without exposing end users to hazards, which is what's most common, frankly, from our experience so far. To further give you a bit more of intuition of what we do, here's a couple of use cases or case studies we have been able to disclose. And most of the cases were very limited with what we can disclose, because obviously some of the information we do handle is sensitive. But this, in this case, the situation allowed us to do it, and we are very thankful about it. The first one, which you have in your left, is a threat model. This is a defensive approach. It entails performing a theoretical study of, in this case, pick and place manipulator, where we studied the threat landscape. We provided the customer an intuition of what are the threats this robot was subject to. And with that, this customer could be essentially more prepared to tackle, mitigate security flaws, and design better their security architecture. The second one was an offensive exercise. We attacked Universal Robots robot. I will explain later about this later on, but essentially it was a penetration testing exercise, which led to more than 80 vulnerabilities, which surprisingly were actually not that many based on what we thought could be found. So more on that later. The presentation here will focus around a main use case, which I will introduce now. And I really thought a lot about which use case I should bring to all of you. And I decided to bring you an industrial use case for many reasons. The first one is that from my personal experience, I did not barely get exposed to industrial use cases while researching, which was, well, unfortunate. The second one is because it's what we've been doing lately. We've been very heavily interacting, cooperating, collaborating with lots of industrial players. And also because it presents a very interesting scenario with multiple levels and tons of insider and outsider potential attackers and entry points. This picture has been drawn based on a number of different norms, standards, and special publications. In particular, you have here one of them listed, which is the NIST Special Publication 882, which provides a series of recommendations of how industrial control systems should be protected. In a nutshell, it pictures recommends to establish 5 levels of security. I'm actually going to make this smaller. There we go. And starting from the top, level 4 is what's typically known as the IT world or the IT network. This is where most of your developers, your colleagues performing finance, HR, or common activities in a company, in an enterprise, do. It is also the network that directly interfaces with the cloud or the internet, of course, via protection systems and firewalling systems, but certainly one that has a number of entry points, such as that particular one. It is also a level that typically includes security systems or entities such as a SOC or a CM. Below that level, below level 4, we have level 3, operations. And this is an interesting level that exposes resources or entities to both the IT world, level 4, and the ones below, level 3, which is what's commonly accepted by some sources as the operational technology or the OT world. I will not get into discussions because some sources consider level 3 as part of the OT world, some others don't. I will just simply essentially inform that level 3 is a boundary, also known as the demilitarized zone, where both IT systems and OT systems are able to access some of these resources to ensure cooperation, interoperability, and other activities within an enterprise that has an industrial area or site attached to it. Level 2, the process network, is where we see most of the elements, entities controlling the overall industrial process. Typically, we have control stations, we have HMIs, we have SCADA systems, and other related devices. You'll see that I've also drawn over there a ROS network. The ROS network is actually across different levels. It can go even down to level 1 from up to level 3. And in this case, it's not drawn in this figure in red, which represents the ROS network, but easily the ROS network could also go up to level 4, the IT network. So as you can see, there is lots of crossing between boundaries, and this already implies decent amount of work, security work on segmentation and segregation. For each different level, we need to take into account the corresponding segmentations and segregations. Below level 2, we have the control network level. Over here, we typically have systems that are dedicated to particular control activities. It could be a collaborative robot, such as in this case, one of the universal robots robot, or it could be a PLC for dedicated machinery control. And finally, we have the field network level. This is where we have the machinery or the mechanics of the robots. And note, we have separated the mechanics of the robot, in this case, the manipulator itself, from the controller and from the control station. Again, I've presented here a couple of scenarios, one with a control station, one without it, but it very much depends of the particular setup. We have encountered a number of them. One thing I can share is that across lots of different setups we are inspecting in cooperation with clients, it is very rare to find industrial architectures that present these 5 levels, these 5 network levels. Most of them present 2, some present 3, and the ones that present 4 are very rare so far. And I'm speaking across customers and also across sizes, from small to big companies. Actually, in some cases, we found reasonably big companies with very concerning industrial architecture. Again, this is what norms and official special publications and documents recommend as the appropriate architecture to secure network based on perimeters, based on particularly segmentation and segregation. But can we get it even more secure? Well, thankfully we can, and there are existing solutions for doing that. In particular, I'm mentioning here one of such, the Kaspersky Industrial Cybersecurity Solution, or KICS for short. This solution attaches to the network, monitors network interaction, and detects potential flaws, threats into the overall industrial control system, and flags them and notifies correspondingly. As you can see, it attaches to most of the network elements, but it can also attach to some of the endpoints. You can see at the bottom over here, let me actually signal it for you guys. Let me just read it be. So we can see over here how it's connected to a PLC, right? And in this case, this solution, again, it does things at the network level. What's doing with the PLC is not protecting the endpoint from the inside. What's doing is solely monitoring the integrity of the actually logic of the PLC, the code, and just ensuring that it hasn't been tampered. But again, very interesting approach, but that sits at the network level solely. Now, going back to the slides, let me check how much time I have. All right, let me try to get it right this time, guys. If we take a look at robotics, we realize that monitoring things at the network level is just simply not enough. For example, if we take the assumption that control station S5 in this case is compromised, regardless of what KICS solution here does, a cyber criminal can easily take control of the robot. It might even not get detected because the machine itself doesn't need to make any particular indications over the network. Because these solutions are not connected to the endpoints specifically, not specifically with robots and not with most of the endpoints actually. And again, it cannot be even detected, of course, not stopped at all. And this is one of the terrible flaws that we are observing in robotics, at least for that's been happening for a lot of time, which is that manufacturers care solely about safety. Being safety, that activity that ensures that the robot does not harm its environment. However, if the environment itself affects the robot, then how can you really ensure that the robot's gonna stay safe, right? And this is the difference between security and safety. And it's also the big mistake that we as a field in robotics are not attacking directly, which is that security needs to come first. Security needs to be ensured at the robot level. Unfortunately, this is what's happening already at the standardization level. Many of the existing standards for safety, such as this one, 10218, the standard for collaborative robots, collaborative robot manipulators in particular, is actually changing towards requesting vendors, manufacturers to care about cybersecurity. Fortunately, it's slowly changing, but not as much as certainly we in security would like to. And that's why I essentially brought this here, because there's lots of misunderstandings. And in some cases, lots of manufacturers don't do much for clarifying this misunderstanding. Here, with simple words, we typically refer to safety as protecting the environment from a given robot, whereas security is actually the other way around, protecting a given robot from a given environment. Now, if you don't have security, logic will tell you that it's very hard or impossible to ensure safety. And this is the baseline we adopt. And this is also what brings us to the conclusion that robots need to be protected from cyber threats from the inside to make sure they operate safely. And it's also what leads us to realize that existing cybersecurity solutions for industrial control systems, and in particular for robots sitting in OT environments, are simply just not enough to make sure that these robots present hazards. And if they do present hazards, eventually they could cause human damages, which of course are the worst case scenario in this setup and in any setup, to be honest. The situation is actually worse because it's just not that architecture-wise we have a problem. Even the devices themselves, the robots themselves, have a huge flaw, a security flaw, many flaws. In fact, with this exercise that we conducted a couple of months ago, we demonstrated how in a week, in just 5 working days, we found more than 86 vulnerabilities, more than 86 exploitable avenues of entering this particular robot of universal robots. And the worst is that we identified many more flaws that unfortunately we didn't have time to triage, but that certainly present an entry point for other cyber criminals. This all builds together into what commonly has been defined as the castle-and-moat architecture approach in security, which we bring to robotics. We did not coin this. Castle-and-moat has been used in lots of different domains, particularly in IT for many years. Also in OT, what I presented, as you will see right now, is a castle-and-moat architecture, actually. Sorry. And it is essentially an architecture that assumes that such as old castles, there is barrier, there is a big wall with a moat potentially that protects insiders from outsiders. But once you're inside, you're fully trusted. This translates to perimeters that once crossed, your system is completely compromised. As I was essentially pitching before, if any of the internal subsystems within the OT area are compromised, this will directly affect or may affect robots getting compromised, which are a very sensitive part of the overall industrial process. And it's even worse. It's just not acceptable that just because S5 is compromised, such as I essentially depict in this figure, since everything within the internal boundary is trusted, I don't only will get access and capabilities to interact as I want with the C3 and with R3, the robot 3, but I also will be able to command at desire other robots through other controllers, which is a huge issue. And this especially becomes possible because, as I explained just before, these robots are fully vulnerable. It takes very little effort to command them. So especially because of this, it is unacceptable that this castle-and-moat approach is deployed in robotics and in industry particularly, because one subsystem, one resource compromise will lead to complete compromise of the overall robotic infrastructure. This led our group, and hopefully some of you as well, to research what's out there, what's being done and used to try to prevent this vulnerable approach. And we arrived into zero trust architecture. This is widely being deployed right now in the IT world and also in the OT world, hopefully soon in robotics. Zero trust is actually a security model, one that makes no trust assumption and demands a strict verification of every single resource interacting over the network, regardless of whether they are sitting inside of the perimeter, if there's a perimeter, or outside of the perimeter. Actually, zero trust allows you to remove perimeters, but this is one of the misconceptions. You can still have a perimeter. Actually, in many cases, we do recommend our clients to still keep their perimeter, but still zero trust allows this additional layer of security by making no trust assumption over the network. Zero trust architecture is a plan that correspondingly implements zero trust concepts. To get you up to speed with Zero Trust, or yeah, I was going to say CTA, but it's more complicated for me. So Zero Trust, I wanted to quickly walk you through 7 principles, and these are covered nicely in the draft and work in progress document from NIST, from the National Institute of Standards and Technology in the USA. Which is the special publication 800-207. I highly encourage you to read this document, to contribute back. We've done so with some of our ideas, and hopefully, if more input is shared, we might be able to bring Zero Trust architectures faster to robotics. Quickly, the first principle, I'm already out of time, just almost. The first principle is that one that essentially requests that all sources of data devices interacting over a network are considered resources. And note that this implies that sensors, actuators, internally within the robot, even if they are not exposed, they are considered resources because they are interacting over a network. Even if it's just I2C or a field bus, doesn't matter. It is a resource and thereby needs to be protected or at least considered. Second principle is that access requests from internal networks, again, I2C potentially, need to meet the exact same requirements as external ones. For example, a cloud system or a robot interacting with the cloud. Those external interactions need to be enforcing the same criteria, the same level of requirements as internal ones. Of course, this is not always feasible, but it is feasible at the group of components level. And we should aim to achieve this to enforce more secure practices in robotics, both inter and intra, at inter and intra communication levels. Very quickly, the third principle essentially asks that trust needs to be authorized before it's granted. This means that if you get authorized to interact with one resource, again, going back to the example, if S5 gets authorized to and gets access control to C3, then that's fine, but this shouldn't grant S5 access to, for example, C6, which is another controller operating another robot. The fourth principle essentially asks or informs that all of the resources need to be controlled and organized based on a central policy which governs the overall interaction. This policy, of course, can be changed dynamically, but still needs to be centrally applicable to the whole infrastructure overall. The fifth one is that systems need to be in their most secure state, and this is a very challenging one because it implies that every single component and subcomponent within a robot or a robot application overall involving different sensors outside of a particular individual robot need to be patched, need to be updated, and this is something we are already not seeing ourselves while essentially providing services. So one that's certainly very challenging, and where solutions need to be deployed and thought. The sixth one is that all resource authentication and authorization is dynamic. This essentially means that there's a constant cycle of access control requests, scans, assessments, policy evaluations, and re-evaluation of trust, where the keys and the overall infrastructure deploys new items for allowing this setup. Of course, there's a compromise between the dynamism and the operational aspects, but this is a must. And last but not least, the fact that the company or the enterprise needs to collect as much information as possible, not just for forensics aspects, but also for ensuring that the communications, the interactions are assessed appropriately and in an online manner. How do we translate all of these principles into the case study, the use case I presented at the very beginning? Well, by introducing two new entities and discarding the traditionally centralized and individually monitored certification authorities. There's, of course, CAs within zero trust architecture, and these ones typically depend or are depending on the PDP, the policy decision point. But for the sake of this particular presentation, I'm just assuming we will not use these centralized CAs, which are managed by a single central control station, which if vulnerated, may compromise the complete architecture of the industry overall. But these central ones are discarded and used in a different setup. How? Well, by ensuring that what's called the PEP, or the policy enforcement point, is the gatekeeper between any interaction between any two resources. And again, I refer to my previous definition of resource. We consider resource any device that's interacting over a network and performing some sort of computation. In this case, the access requests, the authorization and the authentication is done in an untrusted manner via directly the PEP. The PEP needs to be exposed, needs to be accessible to all of the resources. And then this PEP communicates with the PDP, the policy decision point, to enforce the policy. It's only the PDP, the one that evaluates the policy using a number of different data sources that you can see on the left side. Architecturally speaking, the PDP and the PEP don't necessarily need to be connected to the same physical network as the rest of the other resources. They can be separated for security reasons. But again, the PEP needs to be exposed. Following up with the previous example, if the central control station wants to establish secure communications with the controller C6, it would first request the right credentials and artifacts for establishing the communication. This will be dynamically granted, and thereby both parties will be able to establish a trusted, secure communication. If a compromised entity such as S5 in this case wanted to establish such communication, that attempt would be simply discarded because it hasn't been approved by the gatekeeper, by the policy enforcement point. This altogether allows us to establish an architecture for robotics, for robots in an industrial setup where having one particular robot compromised does not compromise the rest of the infrastructure. And this, again, is critical because current robots are very vulnerable. It seems I went out of time once again, but it's much better than past iterations. My team and I are currently implementing this architecture for several robots. We've finished with some of those technologies, some of the ones that I've just exposed, but we are looking forward to cooperate both at the research level as well as the operational one. So if you're interested, just reach out. You have over there my contact details. I'm sure we will be able to find an avenue for collaboration. We definitely need more researchers, roboticists, and security researchers interested in bringing zero trust to robotics. So I really encourage you to reach out if this sounds interesting to you. Last but not least, these are the resources and references I've used to put together this presentation. If you have any questions, feel free to reach out directly. Other than that, stay safe and stay secure. Thank you so much.